Hello everyone, welcome to Aviation Engineering YouTube channel. Today I took a new lesson, EASA Module 6 Aerodynamics, lesson number 1. If you still not subscribe my YouTube channel, please subscribe my YouTube channel, and also don't forget to like, share my videos. So it will be helpful for someone who like for aviation, especially for aircraft maintenance. So from today, I'm going to start the the EASA aerodynamic lesson series. So the first lesson is atmosphere. On the previous lesson, I did about the mathematics. So you can check my previous videos regarding EASA module 1 mathematics, and also I did A320 21, 19, 18 type training some lessons, right? So it is a big series, so I'm continuing zone temperature control, so you can see these videos also, right? Okay, so no need to waste the time, so let's go to the lesson. All right, so today is aerodynamic lesson number 1, atmosphere, right? Atmosphere. So under atmosphere, we will know the atmosphere, and number 2, gas compositions, regions of the atmosphere, temperature, pressure, density, performance ceilings, and gas law, international standard atmosphere, and also the speed. All right, let's go to the first one, is the atmosphere, right? So the gases envelope surrounding the earth is called the atmosphere. So there is no defined upper limit to the atmosphere, but much of this study is limited to the first 60,000 feet where most aviation activity is conducted. All right. Okay, so now the number 2, gas composition, right? Gas composition, the gases are found in the atmosphere in the following proportions by the volume, right? So example, the nitrogen, we can see 78% is available in the atmosphere, and the oxygen is 21%, and the other gases you can see 1% is available. Example, the argon gas, carbon dioxide, water vapor, right? So the oxygen is essential for the sustenance of life and the combustion of materials. Okay, in the context of aviation, oxygen is required for the combustion of fuel, and a deficiency of this gas resulting in complete burning and reduced engine efficiency. All right. So the water vapor is present in the atmosphere in varying proportions and is responsible for the weather around the earth, which in turn affects aircraft operations and performance. Additionally, the presence of water vapor may cause icing of the airframes or engine, which may impair an aircraft performance. All right. Okay, so now the third one is regions of the atmosphere. Regions of the atmosphere. So let's see, the atmosphere is divided into several layers. All right. So the first layer is the troposphere, right? So where the temperature decreases with increase of height. Remember, with increase of height, the temperature is decreases. So in this region, nearly all significant weathers occurs, right? It means the troposphere, right? So the tropopause, the upper limit of the troposphere where the temperature stop decreasing with an increasing of height. The tropopause is therefore the upper limit of significant weather, the first point of lowest temperature, and additionally it is the region for maximum wind strength. All right. So the height of the tropopause varies with altitude. Remember, the height of the tropopause varies with the altitude and season of the year and prevailing weather conditions, with the result that it is usually higher in low altitudes in summer and in fine weather. All right. Okay, so now this one, the typical heights for the tropopause are, so this is the altitude and this is tropopause height. So in the equator, you can see 16 to 17 kilometers. So from the feet, they're given 53,000 to 57,000 feet. So in 45 degrees north to south and 10 to 12 kilometers. And from the poles, North Pole, South Pole, 7.5 to 9 kilometers, 25,000 to 29,000 feet. Right. So, and the third one is, the second one, right, is the atmosphere extends from the tropopause to approximately 50 kilometers AMSL. AMS means above mean sea level, and is characterized by the temperature being steady or increasing with height. All right. So the manosphere extended from 50 kilometers to 80 kilometers. The temperature generally decreases with the height. In the manosphere also, the temperature is generally decreases with the height. All right. So the thermosphere or the ionosphere, where temperature increases with the height. Remember, in the ionosphere or thermosphere, temperature is increases with the height. All right. So now we'll go into the learn the temperature. So A you can call as units. So the temperature scales most used are Celsius and centigrade, right? Fahrenheit and Kelvin or absolute, right? Absolute temperature. So the first two scales are based on the melting point of ice. So being 0 Celsius and 32 Fahrenheit respectively. So 32 Fahrenheit equals 0 Celsius. That is the melting point of ice. All right. So and the boiling point of water being 100 Celsius or 212 Fahrenheit. Being a form of energy, heat is related to the random movements of molecules in substances. If heat is reduced, the molecules become less active, right? The minimum temperature to which a substance can be reduced is approximately minus 273 Celsius, and this is known as absolute zero. Minus 273 Celsius is known as absolute zero, or it means 0 Kelvin, right? So correspondingly, the melting point of ice is equivalent to 273 Kelvin and the boiling point of water to 373 Kelvin. All right. So melting point of ice is equivalent to 273 Kelvin, remember, and the boiling point of water is equivalent to 373 Kelvin. All right. So to convert from one temperature scale to another, the following formula may be used, right? So if you want to convert Celsius to Fahrenheit, Fahrenheit to Kelvin, or Celsius to Kelvin, this formula we can use. See, F equal Y plus 32. So in this situation, we will convert Fahrenheit to Celsius. So Celsius equal 5 divided by 9 and inside the brackets F, it means Fahrenheit minus 32. Or else if you want to convert Celsius into Kelvin, we have to add plus 273. Or else if you want to convert Kelvin to Celsius, you have to minus 273. Okay. Right. So the next one, the temperature variation in the troposphere. Temperature variations in the troposphere, right? So at ground level, in general, the temperature increases with decrease of altitude. Remember, in the ground level, from the ground level, it means this is the grounds from the ground level. With the increase of height, it means, or with the increase of altitude, the temperature is, the temperature increases with the decrease of altitude, or else with the increase of altitude, it means the temperature is decreases. All right. So with increasing altitude, the conductive and convective effects from the earth are reduced, so that temperature will usually decreases with height up to the tropopause. See the figure below. This is the figure. You can see this is the earth and this is the tropopause. Okay, right? Okay, you can see. And typical values of the temperature found at the tropopause are, see the altitude temperature. So equator minus 80 Celsius. Okay, you can see from the equator, this is the tropopause typical temperature is minus 80 Celsius. And next one, 45 degrees north to south, minus 56 Celsius. 45 degrees north to south. See, 45 degrees north to south, minus 56 Celsius. From north and from north to south, this area also minus 56 Celsius. And the poles, I mean south pole, north poles are minus 45 degrees Celsius. Okay, you can see the north pole, south pole, minus 45 degrees Celsius. Therefore, a reversal of temperature with altitude in comparisons to those found at ground level, this is partly because the tropopause is higher at the equator and the temperature decrease in effective over a greater height. All right. Okay, now let's go to the lapse rate. So the temperature decreases with increase of height is refers to as lapse rate. So what is lapse rate? Lapse rate is temperature decreases with increase of height, right? It means when the height is increases, the temperature is decreased. So this is refers to as lapse rate. So a representative value of 2 Celsius divided by 1000 feet is a typical value for the troposphere. And this figure is used as the reference to the Jet Standard Atmosphere, JSA. All right, Jet Standard Atmosphere. So the international standard atmosphere uses the comparable value of 1.98 Celsius over 1000 feet. For meteorological purposes, differentiations between dry, that is not saturated, and saturated adiabatic lapse rate is made, and the value of 3 Celsius over 1000 feet and 1.5 Celsius over 1000 feet respectively are used. The difference of lapse rates are saturated air is caused by the release of latent heat during condensations, thus reducing the temperature change. Just read these things, okay? Alright, so next the temperature and aircraft performance. Temperature and aircraft performance. At a given pressure, an increase of temperature results in reduction of density. Remember, at a given pressure, it means pressure is constant, and increase of temperature. If the temperature is increases, result is the density is decreases, right? It means the pressure is constant and temperature is increases, then density is going to be decreases, right? So firstly, considering airframe performance, a reduction of density, this is the density, the unit, and reduce lift, L. This may be counteracted by increasing the true airspeed, V, to achieve the required amount of lift. Okay, so this is the equations, right? LCL means the coefficient of the lift. So L means the lift, and this is the coefficient of the lift, and half into density over true airspeed squared into S. All right. So the next one is the dynamic pressure is gained at the expenses of an increased takeoff run. Cruising, true airspeed or landing run according to the stage of flights. On the credit side, drag reduces with the increase of temperature. So this is the drag equation. So this is the lift equation. And a piston engine's performance is related to the temperature of the air being drawn into the cylinder head. The higher the temperature, the lower the density and the weight of the fuel-air mixture that can be burned in the combustion chamber. The power output of the engine therefore falls with the increase of temperature. Remember, the power output of the engine therefore falls, right? The power output of the engines therefore falls with increase of temperature. Remember. For propulsion system, piston or jet, thrust equal mass of air into accelerations to which air is subject. So this is an equation. Remember, thrust equal mass of air into acceleration. Thus, an increase of temperature will reduce the mass flow and therefore the thrust. All right. Okay, so the next one, definitions, the pressure. Now we're going to learn the pressure. Pressure, the definition is pressure is the force exerted on a unit area. In a unit area, the force exerted is called as pressure. So pressure equal, the equation is pressure equal force divided by area. Force we can again split into force equal mass into acceleration. So the pressure equal mass into accelerations divided by area. So in the atmosphere, pressure is caused by the mass of gases molecules acting under the force of gravity on a given area. As all modules act under gravity, then the pressure can also be the weight of a column of air on a unit area. Alright, so this is the figure. You can see the unit area, the column of air. So this is the pressure exerted into the earth, alright, or the floor, right? So now the units. The metric units of pressure are dynes per square centimeter, right? The metric unit of pressure are dynes per square meter, where the dynes is the force required to accelerate 1 gram by 1 centimeter per second. The system international units of pressure are Newton. Remember, newtons per square meter is the international unit, where the Newton is the force required to accelerate 1 kilogram by 1 meter per second. The Newton is therefore equal to 10 to the power 5 dynes. Remember, Newton, 1 Newton is equal to the 10 to the power 5 dynes. Just remember these things. Maybe they will ask for the examinations, right? So although largely obsolete, the imperial system of units is still encountered and pressure is expressed in pounds per square inch. So in meteorology, the unit of pressure is the millibar, which is equivalent to the 1000 dynes per square centimeter, right? 1000 dynes per square centimeter. Before the introduction of the millibar, meteorological pressure was measured in terms of the strength of column mercury in barometer that the weight of the atmosphere could support, all right? Okay, so this is the variation of pressure in the atmosphere. So at sea level, pressure generally varies between 950 to 1050 millibar in typical revolving storms and tornadoes. However, pressure may fall much lower With increasing altitude, the mass of overlying air decreases and so the pressure falls. Pressure values of the International Standard Atmosphere are given below. So you can go through this table. Okay, you can pause this video and then you can go through this table. Just get an idea. From the table, it should be noted that at about 18,000 feet, the pressure is half of the sea level value. Let's see, this is 10,000. The pressure is 697 millibar. Or in the 20,000, the pressure is 466 millibar. So in the sea level, the pressure is 1,013. So at 18,000, we can see the pressure will be the half of the this value, right? So that is the thing they explain. So also it should now be apparent that the rate of pressure decreases with height. Remember from this the previous, this table you can get to know the pressure is decreased with the increase of height. The height is not constant. In the first 10,000 feet, the pressure falls at a rate of approximately 1 millibar per 30 feet, but between 30,000 feet and 40,000 feet, the pressure decreases is closer to 1 millibar per 88 feet. Okay. Right, so now then go to the pressure altitude. The altitude at which a given pressure occurs in International Standard Atmosphere is called the pressure altitude. Remember, the altitude at which a given pressure occurs in the International Standard Atmosphere is called the pressure altitude. If, for example, the pressure at the top of Mount Everest were determined as 300.9 millibar, then the pressure altitude would be 30,000 feet, assuming the same mean sea level condition and two columns of air of the same height but differing temperatures. Then the cold air would have a greater mass than the warm air due to the density difference. The pressure of the atmosphere, however, is caused by the mass of overlying molecules on a unit area. The pressure above the column of warm air is therefore higher than that above cold air. Because a higher pressure is found at a lower level, then the pressure altitude above warm air is lower than the pressure altitude above cold air. Alternately, it can be expressed that the true altitude of an aircraft is more than that indicated, assuming the correct mean sea level pressure has been set on the subscale above warm air and less than that indicated above cold air. Okay, so you just read this one and get an idea. Alright, so this is the table. Values are approximately. You can just go through this table and also you can read this paragraph. Then you will have a better idea about the pressure altitude. Alright. So now let's go to the density. Density, the definition is density is the mass per unit volume of substance at a specified temperature and pressure. Remember, definition of the density is the mass. Density is the mass per unit volume of substance at a specified temperature and pressure. So this is the equations for density. Density equal mass into volume. All right. So units density is expressed in grams or kilograms per cubic meter for metric or SI units respectively. The imperial units are pounds per cubic feet. Factors affecting density when considering gases are density equal pressure over gas constant into absolute temperature, right? Okay, so and for a given temperature, therefore an increase of pressure increases density, or at a given pressure a decrease in temperature increases density. Alright, so now let's go to the variation of density in the atmosphere. At a sea level, densities vary between 1.20 and 1.55 kg per cubic meter. The higher values being usually associated with the colder temperatures of high altitudes and the lower values typically of the equator altitudes. Air at lower sea level in the atmosphere is compressed by the mass of the overlying air. With increasing altitudes, the overlying mass reduces and air can now expand, resulting in further reduction of pressure. With increasing altitude, the temperature also increases. Okay, with increasing altitude, the temperature also decreases, but at a rate lower than the pressure. Remember, the rate of decreasing pressure is higher than the rate of decreasing temperature with increasing altitude. Okay, density therefore decreases with the height. Density values of the International Standard Atmosphere are shown below. So you can see the density value, right? So altitude at 40,000, 0.301 is the density, kilograms per cubic meter. Or at 30,000 feet, the density is 0.458 kilograms per cubic meter. Okay, you can see. At about 20,000 feet, right, the density is half the sea level values. We have already seen that the density at sea level tends to be higher at the poles than at the equator. However, at 26,000 feet, the density value is similar at all altitudes, right? Okay. So So now let's go to the variation of density with humidity. The total pressure of the atmosphere is equal to the sum of the individual pressures of the gases. The pressure of moist air is less than that for dry air, and so humidity decreases the total pressure. From the gas equation, it can be seen that the reduction in pressure results in a lower density. The greater the humidity, the lower the density. Alright, so now remember, if there's a humidity is higher, then the density is the greater the humidity, the density is the lower, right? It means humidity, if there's humidity is higher, the density is lower, right? So the density altitude is defined as the altitude in the international standard atmosphere at which a given density is found. Aircraft performance is largely dependent on density altitude as opposed to true or pressure altitude. Density and performance. The effects of density on lift, drag, power, and thrust have been considered in the sections concerning temperature. There are, however, additional effects on density performance above about 300 knots. Air becomes significantly compressed and locally increases the density at much higher speed. This may give a marked increase in drag. And when increasing altitude, this can offset the otherwise reducing drag values. A similar compressibility effect increases drag on a propeller blade, reducing its efficiency, particularly at higher altitudes. Okay. Jet engine performance, however, is enhanced by these compressibility effects as much as mass flow is improved. Right? Okay, now the air density and the human body. Okay, so to the reduced density of air with increasing altitude means that in a given volume of air breathed in, the oxygen content has decreased. Okay, so above 10,000 feet, this reduction leads to hypoxia, right? So this is a little bit important. Its effects ranging from lack of judgment to sleepiness or collapse. According to the height at night, the reduced intake of oxygen impairs night vision and altitudes of 4,000 feet and above. To counter these problems, aircraft operating above 10,000 feet must have an enriched oxygen supply. That's why it's become pressurized. Okay, either in conjunction with pressurized cabin or through face masks. At night, ideally, oxygen should be available from ground level upwards. All right. So now the performance ceiling. Remember, performance ceiling A is service ceiling. This is defined as the altitude at which the rate of climb of an aircraft falls to a specified figure, usually 100 feet per minute. Okay, just go through this one because these kind of things can be asked for the examination. So absolute ceiling. The absolute ceiling is the altitude at which the rate of climb of an aircraft falls to 0. And piston engine aircraft, for such aircraft operating at 26,000 feet, then the improved atmospheric density found in winter is high altitudes will give the highest ceiling. And the jet engine aircraft, as most jet engine aircraft operate about 26,000 feet, then the best performance ceiling will be found at the highest tropopause and lowest temperature, okay, in summer and at lower altitudes. Now the gas laws. Okay, this is also very important. From this section, I think for the year's examination, mostly they will ask about 2 to 3 questions. And the gas law, from the gas law, they will definitely ask 1 question or 2 questions, right? So the introductions, whistle air is not an ideal gas, right? It goes conform within close limits to the result of Boyle's and Charles' law, right? So the Boyle's law, you remember the Boyle's law, the volume V of the given mass of gas at constant temperature is inversely proportional to the pressure, right? See, V it means volume is inversely proportional to the pressure in a given volume. Okay, sorry, the volume of the given mass of gas is constant temperature. Yeah, the temperature is constant. In temperature constant situation, the volume is inversely proportional to the pressure. That is called the Boyle's law, right? So this can be expressed as in this form: P1 V1 equal P2 V2, right? So you can just go through this one. And the next one, Charles' law, and the volume of given mass of a gas at constant pressure, right? In Charles' law, the constant is pressure, and in Boyle's law, the constant is temperature, right? So increases by 1/273 of its volume at 0 Celsius for every 1 Celsius rise in the temperature. So in the Charles' law, in a given the constant pressure, volume is rise in temperature. So V into K, or V divided by K equal constants, right? So it means volume is directly proportional to the temperature in a given pressure. So that is the Charles law. That can be alternatively expressed below, is also useful. V1 divided by K1 or V2 divided by K2. K means the temperature. Kelvin they will express as Kelvin, right? So this is the temperature. So combines Boyle's and Charles law equations. The result of both laws may be combined in one equation expressing the behavior of a gas under varying conditions of pressure, volume, and temperature. So P1, V1. This is the combinations. Charles and Boyle's law combination. So this is the combined Boyle's and Charles law. So the P1 P1 into V1, V2 divided by K equal P2 into V2 divided by. Sorry, this one is V1, right? P1 into V1 divided by K1 equal P2 into V2 divided by K2. This is the combined Boyle's and Charles law. So these gas laws, from these gas laws, for the IAS examination, they can ask some questions for you, right? Okay, so the next one, International Standard Atmosphere. In order to provide a datum for aircraft performance comparison and instruments calibrations, and assumed set of conditions has been determined. While is representative, these conditions do not necessarily reflect actual conditions in the atmosphere. The values used are listed below. The temperature 15 Celsius at a mean sea level and decreasing at 1.98 Celsius per 1000 feet to 36,090 feet 11 kilometers, where the temperature remains constant at minus 56.5 Celsius until 65,617 feet or 20 kilometers. Pressure is 1013.25 millibar at mean sea level. Remember this one. And density is 1.225 kilograms per cubic meter at mean sea level. This is the International Standard Atmospheric Range. Okay. Right. So next one is, the last one is speed. So indicated airspeed, IAS. The dynamic pressure of air against a vehicle or indicated airspeed is equal to the P into V2, where the P is density and V is true airspeed. Okay, V1 and the density, and it means V1 into density into V2, right? True airspeed. And airspeed indicator calibrated to ISA, International Standard Atmosphere mean sea level conditions, records the dynamic pressure as a speed. If, for example, the indicated reading were 200 knots, then it means that the dynamic pressure is the same as it would be at a true airspeed 200 knots at standard conditions at mean sea level. Alright. So next one, rectified airspeed, RAS. So rectified airspeed is the indicated airspeed corrected for instruments and position errors. Right. Next, the equivalent airspeed, the rectified airspeed corrected for compressibility. It should be noted that the compressibility is always subtract quantity. Right. And the next one, true airspeed, the equivalent airspeed is corrected for the density, and the calibrated airspeed. Some airspeed indicators are corrected for mean sea level compressibility. Calibrated airspeed is the value of this reading corrected for instruments and position errors, right? And the Mach number is the ratio of true airspeed to the local speed of sound, right? This is the Mach number. Yeah, that is the end of this lesson. So in this lesson, you learned today the atmosphere, the gas compositions, regions of the atmosphere, temperatures, pressure, density, performance ceiling, gas laws, international standard atmosphere, and also speed, right? So this is the first lesson regarding EASA module 6 aerodynamics. So the next lesson I will going to teach you about aerodynamics and aerofoils. I mean the lesson number 2 and lesson number 2 included aerodynamics and aerofoils. So again, thank you for participating in these lessons, and if you still not subscribe my channel, please subscribe and please share this video with your friends, relatives, and if anyone who wants to learn about aviation, especially EASA examinations. If you are a student, or if you are a mechanic or engineer, someone who wants to get EASA license. So if you wish to do the EASA examinations through any 147 company, so you can follow my YouTube channel and you can get a roughly idea about how the lessons going on. So then you can learn individually and you can pass the examinations very easily. That's all for today. So we will meet on next video. Have a good day for all of you.